The universe is 13.8 billion years old, so how is it possible that we can see galaxies 46 billion light-years away? That shouldn't be possible unless space itself is doing something truly bizarre. If you look up at the night sky, everything you see seems fixed in its place, giving us the sense that the universe is calm and simple. But looks can be misleading. The cosmos is full of powerful processes. The stars you see, the galaxies, and all the light traveling toward us paint a complex picture of our place in space. We are surrounded by what we term the observable universe. This is everything from which light has had time to reach us since the beginning of the universe. Think about this idea for a moment. When we look out into the night, we are literally looking back in time. Light is not instant. It takes time to travel. When the light bounces off me and enters your eye, you see me a few billionths of a second in the past. The further away an object is, the deeper we look into the past. We see the Sun as it was about 8 minutes ago. Even when viewing the Andromeda Galaxy, one of our closest galactic neighbors, we are viewing it as it was roughly 2.5 million years ago. This fundamental principle sets the maximum temporal limit of our observation. Since calculations show that the universe originated approximately 13.8 billion years ago, we might logically expect the limit of our sight to be 13.8 billion light-years. However, the reality is far stranger due to the physics governing space itself. We are actually capable of seeing objects that are currently located an astonishing 46 billion light-years away. Why the massive difference? The explanation lies in the continuous cosmic expansion. The space that separates objects has been stretching throughout the entire 13.8 billion years that light has been traveling toward us. As the light journeyed through this stretching space, the origin point of that light also moved farther away from us. The universe itself has been growing, ensuring that the distance to those most ancient sources is now far greater than the distance the light particle actually covered. This extreme distance defines the maximum extent of our local universe, marking the boundary of what we can, in theory, ever hope to observe. This boundary is dynamic, constantly expanding as the universe ages, and light from slightly more distant regions finally reaches us. The edge of the observable universe is not a place where the cosmos physically ends. It is a limit set by the travel time of light. The tool astronomers use to quantify this vast, ongoing expansion and measure the immense distances to these ancient objects is redshift. This is not merely a change in the light's appearance, it is a fundamental consequence of the physics of expansion. As light traverses the vastness of the cosmos, the space it is traveling through is continually stretching. This stretching causes the physical wavelength of the light itself to increase, just as a wave drawn on a rubber sheet would elongate if the sheet were pulled. Because longer wavelengths correspond to lower energy, the light shifts toward the red end of the electromagnetic spectrum, hence the term redshift. The extent of this redshift directly correlates with the distance of the light source. The longer the light has been traveling, the greater the expansion that has occurred along its path, resulting in a larger redshift when the light finally arrives. Astronomers utilize this principle as a cosmic measuring stick. By analyzing the spectrum of light emitted by distant galaxies, breaking the light down using instruments much like prisms, they identify specific chemical signatures, such as the spectral lines of elements. If those expected spectral lines are shifted toward the red end, it confirms the object is receding due to the expansion of space. The relationship between how red an object appears and its distance is remarkably profound. Even a small redshift, such as 0.1, meaning the light has gotten 10% redder, translates to a distance of roughly 1 billion light-years. The most ancient, earliest galaxies visible to us show much greater redshifts, confirming that their light has traveled for over 10 billion years. The larger the measured redshift, the farther back into the history of the universe we are looking. The continuous nature of this expansion means that every distant object appears to be moving away from us. This observation often leads to the mistaken conclusion that we must be located at the center of the universe. However, this perceived motion is uniform everywhere, implying there is no single center. The expansion is happening to the space between all objects, meaning every point in space would observe every other distant point moving away from it. This idea, often compared to the expansion of a baking loaf of raisin bread, confirms that the universe is isotropic, looking essentially the same in all directions on a large scale. The redshift is the physical proof that space is actively being stretched. While redshift gives us the tool to calculate immense distances, the absolute limit of our sight is set by the most distant event light can possibly escape from. This event gives us the cosmic microwave background radiation. When the universe was incredibly young, in its first 380,000 years, it existed as a plasma so dense and hot that light particles could not travel freely. Photons were constantly absorbed and scattered by free-floating charged particles. The universe was effectively opaque, like being submerged in an incredibly dense fog. Any earlier light generated would have been instantly trapped, meaning no visual information from that time can reach us. Then, about 380,000 years after the beginning, the temperature dropped sufficiently to allow electrons and nuclei to combine, forming neutral atoms. This moment, known as recombination, instantly made the universe transparent. The trapped light was finally released, free to travel across the cosmos. This light, released at the time of transparency, is the most ancient electromagnetic radiation we will ever observe. Because space has expanded dramatically since then, the light is immensely redshifted and cooled, reaching us today as faint thermal microwave radiation coming from every direction, the CMB. The prediction and subsequent discovery of this faint energy provided powerful evidence for the Big Bang theory. Scientists determined that this background energy was thermal radiation left over from the explosion. The work in 1948 that originated the Big Bang theory included calculating the elemental abundances created then. Later work predicted that this leftover radiation should fill the universe, a prediction confirmed in 1963 when the CMB was discovered. The CMB essentially serves as an opaque curtain. It is a physical barrier that prevents us from seeing anything that happened electromagnetically prior to the universe being 380,000 years old. This means that the CMB defines the absolute boundary of our visual cosmic horizon. The CMB is effectively a photograph of the universe at age 380,000 years old. The immense distance of this boundary is now currently calculated to be 46 billion light-years away. Because the CMB represents a definitive physical barrier to our visual capacity, understanding what lies beyond the visible 46 billion light-years requires appealing to models confirmed by physics. The established models of cosmology show that the cosmos does not abruptly end at our horizon. Rather, the material structure of the universe continues outward. The laws governing gravity, matter, and expansion are believed to operate identically in these distant, unobserved regions. Scientists rely heavily on vast computer simulations such as the Millennium Simulation, which input known physics parameters and run forward to model the growth and evolution of structures over cosmic time. These computational models demonstrate that the processes of galaxy and cluster formation, including the development of huge voids in space, persist across distances far beyond our current sight. For example, these models suggest that some of the most extreme galaxies, such as the immense, dead elliptical galaxies that exist today, must have had ancestors that were forming stars at phenomenal rates in the early universe. These distant star-forming galaxies would have been totally obscured by dense clouds of dust, making them invisible to optical telescopes like the Hubble. The consistency between these simulations and the structures we observe nearby grants confidence in the prediction that the fundamental cosmic structures continue outward. Although the light from these distant regions has not had sufficient time to traverse the 46 billion light-years, the material reality of the cosmos continues, characterized by the same massive assemblies of galaxies that we see in our own neighborhood. This recognition that much of the early universe's activity was shrouded by dust prompted astronomers to turn to non-visible light. By studying infrared light, which can penetrate dust and gas like thermal goggles, scientists found that the most extreme star-forming galaxies were previously invisible because their output was entirely absorbed and re-radiated by this dense, obscuring material. Tools like the James Webb Space Telescope, which operates in infrared, are designed specifically to penetrate this veil and reveal the hidden, ancient star factories. The failure of optical telescopes to capture these phenomena proves that the visible spectrum is just a small window into a complex reality. Given the fixed boundary of the CMB for light, the quest to see farther requires harnessing different cosmic messengers. We are fundamentally limited by the nature of light itself when observing the very start of the cosmos. The only messengers predicted by physics that can escape the extreme opacity of the universe in its absolute first moments are neutrinos and, even more profoundly, gravitational waves. Gravitational waves are oscillations in the very structure of space and time. Unlike electromagnetic waves, which rely on charged particles, gravitational waves travel completely unaffected by matter, passing through even the densest material unscathed. Therefore, they carry information directly from the universe's beginning, long before the earliest time neutrinos or photons could escape. Scientists believe that the explosive activity and extreme turbulence that existed during the Big Bang itself should have produced a pervasive background of gravitational waves. The turbulence and rotation that occur during high-energy events, such as the theoretical collapse of stars or cosmic strings colliding, are also expected to produce these ripples. The detection of these primordial waves is considered the ultimate goal of observation, as they would provide data from the universe when it was less than 1 second old. Modern astronomy utilizes sophisticated technologies such as the LIGO Observatory to search for these ripples. Future space-based instruments such as LISA are planned to search for even lower frequency gravitational waves, including those that may have been generated when the universe was only a trillionth of a second old, during the birth of fundamental forces. These observatories offer the potential to push our senses to the final, theoretical limit of time, giving us an entirely new form of astronomy to study the invisible past. Gravitational wave astronomy is essentially a new window onto the universe, analogous to how X-ray or radio astronomy opened up previously hidden information. Let's return to the concept of cosmic expansion and how it dictates the shape and appearance of our observable boundaries. The universal observation that all distant galaxies appear to be receding from us is purely a result of the ongoing stretching of space. This leads directly to the core tenet of modern cosmology. The universe has no center. If the universe had a center, the observed recession speeds would vary in a way that pointed back to that single origin point. However, observations show that the expansion is uniform and equal in all directions on the largest scales. This is consistent with a model where space itself is uniformly expanding, much like a rising loaf of dough. Every raisin in that loaf observes every other raisin moving away from it, without any single raisin being the starting point. This uniform expansion is the reason the current boundary of visibility is so much farther than the distance light has traveled. The light leaving its source 13.8 billion years ago traveled toward us, but the source itself moved with the expanding space, creating a far greater total distance over time. The fact that the expansion is uniform is supported by the smoothness of the most ancient light we see, the cosmic microwave background. This background radiation is uniform across the entire sky, arriving with almost the exact same temperature in every direction. This uniformity is a fundamental confirmation that the universe is highly isotropic and homogeneous on the large scale, meaning it looks the same everywhere with no central point or edge. The theoretical limit of our observation, the cosmic horizon, is perfectly spherical around us because the expansion is uniform in all directions. Since light has traveled for 13.8 billion years, the edge of that spherical volume is precisely the boundary where light left 13.8 billion years ago, a boundary that is now currently 46 billion light-years distant due to the intervening expansion. The shape of the cosmic horizon is a sphere centered on us, purely because we are the observer. Let's focus closely on how redshift, the stretching of light, enables us to classify and study the most energetic objects in the universe, confirming their distance and ancient nature. Light is an electromagnetic wave. The energy of the light is determined by its wavelength. When space expands, the light traveling through it stretches, making the wavelength longer and causing the energy of the light to drop. This makes the light appear redder. For light from distant objects, this redshift is extremely important. Astronomers measure the light from these distant sources using a spectrometer, breaking the light down like a prism into its component colors or wavelengths. They look for specific spectral features, which are unique light signatures produced by certain elements. For example, the earliest scientists used this method to study quasars, which are incredibly luminous, continuous sources of light far away. When the first quasar spectra were studied, the characteristic lines looked familiar, but they were all shifted dramatically to the red. This meant the light had been traveling through expanding space for a very long time. By calculating this redshift, astronomers found that quasars were incredibly distant, many billions of light years away. This confirmed that they were seeing these objects as they existed in the past. The discovery that redshift indicates great distance confirmed the power of looking at the universe in different forms of light, because visible light can travel only through non-obscured space, moving to longer wavelengths like infrared, which can pierce dust and gas, or radio waves became absolutely necessary to study the full extent of cosmic history. Astronomers had found that this tiny shift, the redshift, revealed objects that were incredibly energetic. For a quasar, the core of a massive galaxy, the luminosity was so high that it was equivalent to thousands or even 100,000 times the light of the entire Milky Way. The only way to explain this immense energy output was through the highly efficient process of accretion onto a massive black hole. Thus, redshift did not just tell us how far away things are, it helped confirm the existence and power of the most extreme objects in the universe. The redder the light, the more distance it has crossed, confirming its identity as a messenger from the ancient cosmos. The study of these ancient, distant objects reveals a significant finding. The universe was far more active in the past than it is today. The peak of this cosmic activity, measured through the intense light and redshift of distant sources, occurred roughly 10 billion years ago. Quasars, which are black holes feeding aggressively, were about 100 times more common 10 billion years ago. This period coincided with a peak in star formation, which was also roughly 10 to 20 times greater than modern rates. The light from this ancient, active period confirms that galaxies and their central black holes were growing extremely quickly at the same time. Since that time, the activity has decreased. The reasons for this decline include the general expansion of space, which made galaxy collisions, mergers, less frequent. These mergers were crucial for pushing fresh gas to the centers of galaxies, feeding the black holes efficiently. Additionally, over the entire history of the universe, the gas available for star formation has been steadily consumed. Today, the huge black holes that cause those distant, luminous quasars still exist, but because they have mostly run out of easily accessible fuel, they are much dimmer. This means that the light we see when looking back into the cosmos is showing us a universe that was much more dense, chaotic, and energetic. Our current position means that the light we receive from the most distant visible objects is evidence of this past cosmic violence. To continue observing the universe's full history, we must rely on messages that predate light. Neutrinos can bring information from when the cosmos was 1 second old. Ultimately, the study of gravitational waves promises to reveal the structure and mechanics of the universe when it was only a tiny fraction of a second old. These non-light messengers will push our ability to see farther into the past, past the visible horizon and toward the theoretical edge of time itself. If you want to understand space. Like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. The visible universe shows us a profound history defined by expansion and light travel time, confirming that the limit of our vision is a boundary in time, not space. If you want to explore a scenario that instantly breaks the predictable physics we rely on for everything we observe, click here to watch What If Earth's Rotation Stopped video.